All right, here's some highlights of the machine work that happened on this part. This is a Mitsubishi feed mill, 3 flute, inch and a half diameter. Have it in kind of a long holder because of interferences with the machine. So I'm being pretty conservative with these cuts, and I don't want to go real fast. I want to just have consistency with the, not having to index inserts and putting a lot of heat into the part. Um, you might be hearing a funny sound. It's because I'm blowing air through the tool to use as sort of to cool things off here. In these materials, oftentimes it's better. This is, oh, by the way, this is 4140, and I think it was annealed because it was machining kind of like that. And a lot of times it's better actually to run these materials dry with these kind of tools, with the carbide tools, rather than put coolant on it, because it kind of causes, particularly with a feed mill. In fact, I would say with almost all materials except for very exotic materials, you don't want to run coolant on a feed mill. In all kinds of steels, and probably stainless steels of sorts, like 300 series and stuff like that. When you get into your Inconels and titanium and stuff, yes, you need to run coolant, but other than that, don't run coolant on a feed milling cutter. But I'm not really pushing this tool very hard. It's, like I said, I just don't want to mess with the thing. I just want to start the machine and just let it run, type of thing. And in fact, it roughed this whole part without even having to index the inserts at all. So now we're coming up pretty close to the end of the roughing. And that was roughing out the I guess you might call it the flutes of this part. And then we're going to come in with a 1/2 inch diameter bullnose end mill with a 1/8 inch radius to finish the floor. And I'm actually cutting a little bit of a negative stock allowance on this profile. Basically, I just took a bunch of profiles and patterned them around the part. Now, you could use a pocketing cycle to do this, but if you feed like down the helix like this, it leaves a nicer finish on this kind of a setup rather than trying to feed around like from the center out in a circular pattern, I guess you call it. It feeds it leaves a better finish, and you'll see later on what I'm talking about. But I'm running a negative stock allowance so that I can get up to the end of the radius of the bullnose end mill to match the radius of the wall coming down. It's got a 1/2 inch radius at the base of those walls, and you want to overlap this radius onto that radius. So I had a -1/8 of an inch stock allowance on this tool. Here's what we have after running the finish pass just on the face. I guess you might call this the bottom diameter of this piece. And what I have found when milling steel like this is that it actually works better if you don't use coolant when you're doing something like this. And also, with this type of end mill, is a bull-nosed end mill. And for these kind of milling cycles where you're milling on the OD of a part, like a wrapped milling cycle is what this is. This are wrapped contours and just spaced over and over and over again. It leaves a much better finish. The finish is quite smooth here. You can see a little bit of change right here where I'm going the other direction with those passes, but you can't even hardly feel that at all. This finish is nice, actually quite nice, even though it kind of looks a little. Let me see if I can get closer in here. You can see the passes all right, but they're really hardly anything. And this is about the best way. If you try to do this with like a square-edged sharp corner end mill, the end mill is actually cutting with the face as it's wrapping around these contours, and it leaves ridges along here more so than a bullnosed end mill like this is. This is a 1/2 inch end mill here with an 1/8 inch tip radius on it. And that works better. You could do this with a ball end mill as well, but you got to make a lot more passes with a ball end mill to get the surface completely done. And also, unless you tip the spindle back like this and are milling with the side of the ball end mill, the surface footage is so slow in the middle of the end mill that it actually most of the time causes the end mill to fail, the ball end mill right on the tip of it. Now I'm going to mill these sides of these ribs with a ball end mill with kind of a surfacing cutting style, a 5-axis thing, and I'm tipping it back for this one. So if I rotate this, it's going to be milling in the back, and it's going to be tipped back with the spindle. But I couldn't really tip this one back this much here because up here I'm going to be hitting this part of the spindle, or the not so much a spindle, but see this y-axis, the corner of that on here and up above with the top of the spindle. If it's tipped back this way, it hits the cabinet of the machine up here. So you kind of have to I kind of have to tip it this way as well because I want clearance on the spindle face, although I'm going to put a spacer on the tool holder kind of like this. I don't know if you can see that. That has a capto extension before the end mill holder, or the end mill chuck, I should say. And I'm going to do that as well because I want to have a little more clearance. I don't want to be hitting the spindle face with it tipped back like this on something else. Although in the simulation on the computer, excuse, camera kind of, the simulation on the computer doesn't show it colliding with anything with the holder that long. I'm still going to put one in there for a little bit extra clearance. I've split the program into 3 sections. So it's just doing these 2 inside walls, and then I load another program and do the 3, the other 2, and then the other 2. But I could have just as easily just programmed this section and then rotated 120 degrees with the fixture offset. That would be another way to do it and save in memory in the machine. But I tried to put all the program, the roughing and the finishing here and the finishing of the bottom face all in one, but it was too large for the machine's memory. So I just split it into different programs, and it was kind of better that way, because if I had trouble with any of the tools or anything, I wouldn't have to run a whole program because these kind of programs are very difficult to start in the middle of the program or something, because you kind of got to figure out where you're at to restart it. And so it's better to program and just split it up into smaller chunks in a way, so that if you have trouble, say this tool wears out and you want to change it to another new tool, you can do it at a certain point in the program, and it makes it a little easier to do that anyway. So this area is all finished now, and then we got to do, you know, each one of these, the walls of each one of the ribs here. And it seems like it came out pretty decent. Now, with this kind of cutting, what you want to try to do with the ball end mill is not cut with the tip of the very tip or center of the tool, the tip center, if you will, if you can help it. That's why I've tipped the B-axis back. Now on this one, it wasn't the most ideal, because I had it tipped back kind of this way, and it was more bringing the ball end mill vertical to the cut because of the helix of this rib here. But I didn't have room because of interference issues with the cabinet and the spindle up here to tip it this way. But ideally, if you could do it, it would have been better to tip the ball end mill this way. So I'm cutting with the side of the radius of the ball, and I'm not plunging the center of the tool. I was kind of, in a way, plunging the center of the tool down in there when I'm coming down, and that's not very good with a ball end mill, because there's lots of shavings. Well, there's not enough clearance on the tip of the tool to let the shavings come up through the tip, and you're plunging in, and this can make the end mill fail at the tip of a ball end mill, cutting like this. Back and forth. The climb cut coming up was fine, but when it's coming down, it's pushing the material into the center of the tool, and that also is not good if you can help it. So if you have the ability to tip, like on the back side here, when I was tipping the spindle this way, it was really most ideal. On this wall here, but this one, because of my clearances and stuff on the way the part is set up in the machine, and I can't get that far over this way. If I had this extended out, this is kind of the reason I put that small 3-jaw chuck in this bigger chuck, so that if I have to tip the B-axis back this way, it gives me more clearance up here of the spindle tipped back, hitting the cabinet of the machine. The top of the spindle up there is tipped, and it hits over here. And also this piece, like I said before, right here collides with this over here if you got too short of a tool. So that was part of my problem with this operation, and the reason I have the spindle tipped back this way. So I have more clearance on the chuck, and I don't have to use such a long tool. Like, I could have used the shorter tool than what I actually set up, but I decided to set a little bit longer tool just for that reason. All right, I've had a few comments on previous videos about showing some of the programming aspect in Esprit software. Now, the Esprit software is a, let me open up the features tab here, is a feature-based software. So when you're dealing with anything, you know, with milling contours, first you have to define a feature. So the roughing out of this flute, of this helix, I guess you could call it. You define a feature, they call it a freeform feature, and then you put your cycles onto the features, which this is the roughing cycle. So basically what I did here is this is a 5-axis type cycle, but I've actually I'm going to go back here. I've actually limited the movement of the B-axis in these limits on the toolpath to a certain angle. In this case, it's straight up and down, like a 90-degree angle, because with this feed milling cutter, this turns out to be the best way to do this kind of a roughing cycle. And actually, even though you get kind of an optical illusion, you may have noticed in the video, it looks like this the cutters doing this are following this helix, but actually they're not. If we look at the simulation of this, let's go to the simulation, and I play it. If you look here in this part of the screen, you'll see the y-axis stays on center line of the machine, actually, even though it gives you the illusion that it's following some kind of a down the helix, but it actually isn't. It's staying on center line for most of these kind of cycles, at least for the roughing out like this, and these wrapped contours is the way I finished this. Now, I had a commenter on Instagram saying that the finish would be better, and I've already talked about this in the video, the previous part of the video that you saw, but that the finish would be better if I use a cycle like this. This is a roughing cycle, but you can actually do a floor finish in this. But if you feed with the rotary axis like this, an end mill will leave it won't leave as good a finish on a wrapped kind of a cylindrical surface as this kind of doing this kind of things. Although this is a little bit more difficult to program, because basically I took this. Actually, what I did to start this is I actually selected this shape here and just made a wrapped contour on it, and then I positioned it down here by rotating it, and then I just copied it a bunch of times. I think it took like 32 times to get up to the end of the radius. And actually I'm slightly overcutting this into the I don't know if you can see it here, but I want to cut a negative stock allowance of the radius of the end mill, which happens to be 1/8 of an inch in this case, so that I actually get the flat face of the end of the bullnose end mill to the end of the corner radius, which the 1/2 inch corner radius of this wall of the rib here. So then I just came over this way and I did a few copies down until I got to the same position on this side of it. I kind of wanted, the idea was to climb mill both sides of it, I guess you might say. So that's basically all of the, I don't know if I could select all these here, doing the finish. And doing it like this actually leaves a better finish, even though the finish, I mean, I probably could have run a lot higher surface footage on the tool, but I was being kind of conservative here. I didn't want to have trouble with the tools, and I wanted to run it dry for the purpose of the video, but in reality, like I said in the video, running on soft steel, this is the material I believe was 4140, and I don't think it had much of a heat treat, if any. It might have been annealed. And it was machining pretty easily, and I could run it dry. And it turns out running dry with this kind of a steel, with these kind of tools, actually works better than coolant. Coolant tends to, I don't know, it makes the carbide fracture due to heat changes in the carbide. And so the tools last better if you run with no coolant. So that's the roughing cycle, and I just copied it 2 more times. You might notice if you look in the upper left of the screen here, there's these little padlocks on these copies. In a spree, you can't really go editing the copies that you made here if you do it on this kind of a cycle, so you have to do all your edits on this, get it the way you want, and then rotate it around, copy it 120 degrees in this case twice. If you want to make a change, you kind of got to delete these copies and then make your change and then copy it again. It's not really that big a deal, but that's the way that kind of works. And the same with these wall finishes on the walls of these ribs was the same way. I made those and then I copied them around. And like I said in the video on the machining, the size of this program from my machine is kind of an older machine, and it doesn't have a lot of memory in the machining side of the machine. It has plenty it has a hard drive, and you can put the programs on there and just move them back and forth, but the actual machine memory that the machine uses to machine with is only about 2 megabytes, I believe. So I couldn't fit this program in the memory, so I had to break it up into smaller cycles. And actually, sometimes I do that anyway, because if I had trouble with this tool and I don't want to run this whole cycle all over again, like all the way around the part, I can break it up into smaller sections, and then I can restart the program in certain areas. So I oftentimes do that anyway. So the finishing floor, if you will, of this, like I said earlier, is actually a wrapped contour of this, and then these cycles here that finish the walls are 5-axis cycles. But again, I've kind of restricted the orientation of the tool in the B-axis. Now these two movements, for some reason I couldn't get rid of them on this cycle. I fiddled with it. You can fiddle with this angle, this 75 degrees, which is what I'm tipping the B-axis at, and sometimes you can get rid of those. And in fact, on this side of it, I was able to get rid of all of them. Not that big a deal, really. Didn't cause any problem. It's just that you like to get your toolpath as nice as you can. And like I said, I was trying to keep the tip of the ball end mill off the work, if you will. If I open one of these up, you can see the angle of the tool like you saw in the video, and the angle on this side of the rib is much better than on the other side, which I couldn't, due to the setup constraints on the machine itself. I couldn't tip this tool enough the other direction to make it even better. But so these are just 5-axis finishing in the Z-axis, they call it. But you can manipulate the angles of the tool a little bit so you can get it to kind of go where you want it. So that's, I don't know if you can hear me with these air hoses. They're blowing air hoses and everything over here. But I'm also running pretty kind of slowish feeds and speeds here, because I didn't want to have a lot of trouble with the tools and the tooling on this. I just want to let it run, and so that's what I was doing here. So you can see kind of if I play this, you can kind of see it on the simulation. If I turn on the cabinet of the machine, you can see it there. And then in this Esprit software, this Esprit TNG, it's pretty accurate if you define all these things very accurately. You notice I have the tool holder without the extension on it here too. But if you define everything very accurately, you're not going to have any collisions that you don't see in the software on the machine itself. I haven't run the tailstock up here. There's a tailstock here because it really isn't necessary for the purpose of programming, and I'm not getting really close to the tailstock in this case. Sometimes I run it up there if I'm doing some turning or something close to the tail center, but in this case I'm not, so I didn't need it up there. But anyway, that's a little bit of the software, and how I did it here. It's not really I'm not going to get into a lot of detail with this, because there's very few people that actually use this software. There are a few people that, like I said, made comments on they want to see a little bit of programming aspect of it, except for the actual settings and everything. This is the cycles that I used. All right, here we are back with the finished part. want you to notice something here. Maybe you can see it, maybe you can, maybe you can't, I don't know. But you see the finish on this is much better because the end mill is actually at a more optimal angle. The ball end mill, it was using the side of the ball more so than this. I don't know if you can see that here or not. Let's see. I can. Maybe, I don't know. But this, because the end mill was kind of more perpendicular to the surface here because of the nature of my setup, it tended to leave a little bit less of a nice finish, I guess you could call it. This one's much better. So when you do milling like this with a ball end mill, it's always, like I said before, better to tip it at an angle so that you're cutting with the portion of the ball and not towards the tip of the tool. This was more almost perpendicular, not quite, it was about like this to the surface, where this one was running at an angle more like this, and it leaves a little nicer finish. The surface footage of the tool is a little bit higher here because it's out on a bigger diameter of the ball than here, and also this is kind of cutting with the tip of the tool, which has less clearance for shavings and everything to get out, like I said earlier. But anyway, this is the finished size. This is supposed to be let's see if it's close here, some sort, 3 inches across, which is perpendicular to the center line, plus or minus 100 thousandths. It's not a close tolerance, but well, here would be even a better place to try to check it. Pretty close. Well within tolerance. So all the milling is done on this. Get a little bit of deburring on these sharp corners, and maybe hit it with a Scotch-Brite wheel a little bit, or a pad on an angle grinder or something. Knock off a little bit of this. Well, it's not really that bad. It probably could be left alone even. But anyway, this is the finished part as per their drawing. Like I say, I think they put some hard laser hard cladding on these ribs here, whatever you call them, the way this part is used.